You ever notice that pretty much every great invention isn't just some brilliant idea that pops out of nowhere? Nope, it's almost always a hard-won victory over a really, really tough problem, a constraint. In this explainer, we're going to dive into how these invisible walls don't just stop us, they actually force us to get creative and, build the future.
It all starts with a super simple question, one I'm sure you've tried yourself. You take two identical pieces of paper. One, you crumple up into a tight little ball. The other, you fold into a sleek airplane. You throw them both. So why does the plane just glide while the ball plummets?
Well, the answer is an invisible wall, a force that's literally all around us, all the time, constantly pushing back. It's a fundamental constraint that engineers have been battling for over a century, and learning how to beat it has completely reshaped our world.
So what is this invisible wall? It's air resistance. And the whole science of fighting it is called aerodynamics. Seriously, for anything that moves, a car, a plane, you name it, this is the first and biggest challenge. How do you punch a hole through the air as efficiently as you possibly can? And you can really see that battle play out over time right here. On the left, we've got the 1934 Chrysler Airflow. This was one of the very first mass-produced cars that took this stuff seriously. Now compare that to the crazy-looking Mercedes concept on the right. The shapes are just radically different, and they were sculpted by decades of learning how to tame the wind.
So here's the bottom line. An engine has to use power to shove a car through that wall of air. And power needs fuel, right? Fuel costs money. So the whole science of aerodynamics is about one thing, reducing an object's drag, making it slipperier. Less drag means the engine works less, which means, you guessed it, better fuel efficiency. It really is that simple.
For decades, the main tool for this fight was the wind tunnel. These things are massive, they're super expensive, and they're slow. But then a new technology came along that basically put the power of a wind tunnel right on an engineer's desk, and it completely changed the game.
Okay, so take this car, a Mini Cooper S from the early 2000s. Not long ago, a university student decided to run a little experiment. The question was, could they, just using modern software on a regular laptop, replicate the super complex aerodynamic work that a massive car company did 20 years ago?
The leap in technology here is just incredible. 20 years ago, designing a car like that Mini, it meant building expensive physical models and running what were, by today's standards, pretty basic computer simulations. Today, a single student has access to powerful software that can do the exact same job, but faster and in way more detail.
And that software is called Computational Fluid Dynamics, or CFD. The easiest way to think about it is as a virtual wind tunnel. It lets designers test hundreds of tiny changes to a car's shape without ever having to build a single physical thing. It completely overcame the huge constraints of time and money that used to rule car design.
And here it is. This is the payoff. Look at the image on the left. That's a manufacturer's 2D simulation from back when the Mini was designed, showing some basic airflow. Okay, now look at the right. That's the super detailed 3D mesh model the student built. The leap in complexity and just how precise it is, it's staggering.
So what was the conclusion? It's incredible. The student, working all by themselves, was able to get the same results as a major car manufacturer. And that's exactly what new tech does. It shatters old constraints, it democratizes innovation, and it puts these unbelievably powerful tools in the hands of way more people.
But what happens when the constraint isn't something as thin as air, but something much, much denser, like water? We've seen a digital solution. Now let's check out a wild, physical one. The age-old problem with amphibious cars wasn't getting them to float. That's the easy part. It was making them actually move well. See, in water, a car's wheels are basically just anchors. They create enormous drag and turn the whole thing into a clumsy, slow-moving raft. The solution was the Aquata, a vehicle designed to solve that one huge physical constraint with some truly brilliant engineering.
And the solution is pure spy movie magic. I'm not kidding. You drive it straight to the water's edge, you press one button, and about 5 seconds, poof! The wheels retract up into the car's body. They just disappear into the wheel wells. And at the exact same time, a powerful water jet drive kicks in, and it instantly transforms from a sports car into a real-deal speedboat.
And the performance is no joke. On land, it can hit 160 kilometers per hour. But in the water, it gets up to 50 kilometers per hour. Now, that might not sound super fast, but trust me, on water, that is more than fast enough to get up on a plane and even tow a water skier. It totally conquered the physical barrier of wheel drag. So far, we've seen technology win every time. But that's not always how the story goes. Sometimes the constraints, those invisible walls, they're just too strong to break through.
Let's go back to the 1950s, the heart of the atomic age. Engineers were dreaming of the ultimate car, and I mean ultimate. It would be powered by its own miniature atomic reactor. Just imagine that for a second. A car that would almost never need to be refueled and would produce zero emissions. It was this incredible promise of clean, limitless power.
But the constraints were just insurmountable. First, the lead shielding you'd need to protect people from radiation would have made the car impossibly heavy. Then there's the really big one. A car crash could turn into a small-scale nuclear disaster. And that's before you even think about getting rid of radioactive waste or, just the general public being terrified. The laws of physics and the rules of society, they built a wall that was just too high to climb.
I love how one of our sources put it, pretty humorously. Okay, so many of these initial designs were quite rightly discarded. At least we now know some really bad ideas. And that's the thing. Even in failure, we learned something valuable. We learned where the truly hard problems are.
So where does all of this leave us today? Well, all of these past battles, with air, with water, with physics, and with society, they're all kind of converging on one ultimate technological challenge.
Of course, I'm talking about the dream of the flying car, and its checklist of constraints is just epic. For control, they have to be autonomous, because, let's be real, most of us can't pilot an aircraft. Environmentally, they have to be quiet and non-polluting. The cost is a massive barrier. You need incredibly advanced tech. And then there's regulation. How in the world do you manage thousands of these things flying over crowded cities?
So you see, the flying car isn't just one problem to solve. It's all of them, all at once. It's an aerodynamic problem, a computational problem, a physical problem of power and weight, and a massive societal problem of safety and regulation. It's basically the final exam for vehicle engineering.
So as we've seen, innovation isn't random. It follows a pattern. A clear constraint demands a clever solution. Whether that's using computer power to tame the wind, or ingenious mechanics to counter water, or just getting a reality check from the laws of physics. These walls don't just block the path. They actually show us where the new paths need to be built. Which really leaves us wondering, what's the next invisible wall we're all about to break through?